Okay, the last thing we talked about in class was once we know how to find critical values, which we know are places where the derivative is either 0 or undefined, we want to learn how we classify whether or not those critical values are local extrema. So is it a local maximum or is it a local minimum? So we talked about the fact that where the derivative is positive, so you think about like what it means for the derivative to be positive, ways that the derivative can be positive, means at any given point the tangent line is positive, slope is positive, sorry. So those are going to be increasing functions. Where the derivative is negative, the function will be decreasing. And then, of course, where the derivative is 0, then that means the function is constant on that interval. This is, of course, if it's for all values. Okay, so to find intervals where the function is increasing or decreasing, first we know we locate the critical numbers. And then we use these numbers to determine our intervals. We talked about the fact that once you sort of have found your critical numbers, so say you have a critical value here and a critical value here and maybe even another one here, you would test each of these intervals, 1, 2, 3, 4 intervals, the way I've drawn it, and whether the derivative is positive or negative in this interval it'll stay that way for the entire interval. So we just pick a value in each of these numbers and check to see if the derivative is positive or negative, and that tells us if it's increasing or decreasing. Okay, so that's what it says right here. And then we work through number 22 in class. So let's look at this next one. So first, to find the intervals for which the function is increasing or not, we start by finding the critical values. So remember, those are places where the derivative is either 0 or undefined. So how do I find the derivative? So we have a product of a polynomial times an exponential. So we use product rule on that. So we have the derivative of the first times the second, leave it alone, plus we leave the first expression alone, times the derivative of the second. Derivative of the second thing is e to the x. So we're looking for where is this derivative either 0 or undefined. I've got a polynomial times an exponential. This is never going to be undefined, but I just really need to know where is it 0. So when in doubt, we want to factor, because we're trying to find where it's 0. So we want to factor out an e to the x, which is our greatest common factor, and we're left with the rest of this stuff. So I'm going to rewrite it in an order that we're more familiar with. We want to know where is this equal to 0. So zero product property says that if we have a product of two things and the result is 0, it must be that either one or the other is equal to 0. So we've got two choices. Either e to the x is 0, which never happens. Algebraically, we can see that because if we take the natural log of both sides, that's what cancels out the e to the x. And x is equal to the natural log of 0, but that's undefined. The other way to have solved that is just graphically. Think about it. What does e to the x look like? E to the x looks like this and has a horizontal asymptote at the x-axis. And so it never crosses the x-axis. It's never 0. So we're not getting any critical values there. Here we're going to factor x plus 3, x minus 1 should work. And so zero product property says either x plus 3 is 0 or x minus 1 is 0. So we get two critical values. X is negative 3 and x equals 1. So we have our critical points. I'm just picturing them on my number line, negative 3, and it doesn't really even matter if I draw a scale. I'm looking in these intervals. So what I want to now do is pick a value. So pick a point. Pick an x less than negative 3. So pick any number you want. Let's say negative 5. So x equals negative 5. And we evaluate the derivative f prime at that point and look just to see what's the sign of it. Is it positive or negative? So e to the negative 5 is going to be a positive number. And then I've got negative 5 squared is 25. So 25, I'm going to write this small, plus 2 times negative 5 is a negative 10, and then minus 3. So 25 minus 10 minus 3, that's still going to be a positive number times a positive number. So I get a positive result. Okay, so I'm just going to write a plus sign here to remind myself that it's positive. This is where the derivative, I should write the derivative is positive. So what does it mean for the derivative to be positive? That means the function itself, f, is increasing. Okay, so if I'm writing my answer down here where the function is increasing, it's going to be from negative infinity up to negative 3, not including negative 3, because at negative 3 we know the derivative is 0. Okay, now we pick some point between -3 and 1. So we want to pick a point between -3 and 1. So let's say 0. That's an easy one. Okay, we put it back in. What is the derivative at 0? So e to the 0 is 1 times, if I have 0 plus 0 minus 3, that's a negative number. A positive times a negative, we get a negative result. So this is negative. So the derivative is negative, which tells us that the function is decreasing. So the function is decreasing on the interval from -3 to +1. Again, not including the endpoints. All right, and then finally we pick a value, pick x greater than 1. So let's see, how about 2? So e to the 2 is positive. 2 squared is going to be 4 plus 8 minus 3. Okay, so that's going to be a positive number as well. By the way, on any of these calculations, if you don't follow or if I'm going too fast, then it's your job to go back and double check me, right? So you have, the point is for you to understand what I'm doing here. The derivative is positive, so that means the function is increasing. So we include the part from 1 to infinity with the increasing part. Okay, so if all I cared about was where they're increasing or decreasing, which is technically all they asked for here, we'd be done. We talked in class about how this really does give us more information, though. We know the derivative is not undefined anywhere. It's 0 here. It's 0 at these points here. So if I have a function that's increasing and then decreasing, it must hit a local max at an x value of -3, -3 comma something. And then I'm going from decreasing to increasing. So at this point down here, I'm hitting a local minimum at 1 comma something. Now to get the something, I need to plug that back into my original function. So let's see, if I put -3 back in, I get 9 minus 3 is 6, and then 6e to the -3. I'm going to leave that as 6e to the -3 because that's exact form. Sorry, that's hard to read. That says 6e to the -3. So there's my local max. Again, this was not asked in this problem, but let's go ahead and do it anyway. And the local minimum would be when x is 1, so that's 1 minus 3 is -2. So -2 e to the 1. And again, I'm going to just write that in terms of e as an exact answer. So my local minimum would be here. Okay, so that's more information than we needed, but that gets us ready to understand the first derivative test. So first we have a definition which says a function is called strictly monotonic on an interval if it's either increasing on the entire interval or decreasing on the entire interval. So for example, x cubed is monotonic, right? Because it's always increasing, even if I'm coming from the negative direction, it's just always increasing. Why do we define that? Well, that's just so that you realize that we don't always have to have, so we could have a critical value, and I know this isn't drawn very clearly, but if I were doing what I just did above for this example for x cubed, I'd have a critical value at 0. And in both cases, I would get that the derivative was positive. And so this wouldn't be a maximum or minimum. The whole thing would always be increasing. So we would say it would be increasing for all real values, all real numbers. So I want you to realize that that certainly can happen. Okay, so let's explicitly state the first derivative test, which again, I know we talked about a little bit. So the idea is we're always starting with these critical numbers, and then we want to identify whether they are local max or min. So if f prime changes from negative to positive, so this is like thinking of f is going, so this is like saying f going from decreasing to f increasing. Right? If you're going from decreasing to increasing, then we have a local minimum or relative minimum of f at there. And if the derivative goes from positive, so that's like f increasing to f decreasing, then of course that's going to be a local maximum, right? So we've got increasing. Oh, did I say that? I said that backwards. Okay, say that again. Sorry. If we go from increasing to decreasing, decreasing, that's when we have a maximum. And if we go from decreasing to increasing, that's when we have a local minimum. Okay, it's written correctly. I just said something wrong. Sorry. Notice that we can have other choices. It might go from increasing to increasing, in which case we have neither situation, right? It's not a local max or a local min. Or if it just stays decreasing the entire time, that's also not a local max or min. But those points are it's still a critical value at C. And then the other thing that I want to remind you of is that if you have a place where, let's say the critical value is because we have a vertical asymptote, so like y equals 1 over x, right? If I were doing this on my sort of chart, I would get my critical value at 0, and I would get that the derivative is negative and again negative. which I know we wouldn't have then. All right, so that's a bad example. Let me change it. Y equals 1 over x squared. Okay, hold on, let's see. Sorry, hold on a second. Let's erase this piece and erase that. Okay, y equals 1 over x squared. I would get increasing and then decreasing for my function. And so you might accidentally think that you've got a local maximum, but you have to be careful because at 0 the derivative was undefined because the function was undefined. So you might even want to draw in like a little vertical asymptote to remind you that just because we're going from increasing to decreasing doesn't mean we have a local max here. So be on the lookout for sort of little places where you have exceptions. Okay, so let's go ahead and wait. So this I think is the same. Is this the exact same problem we just did? Yes. Okay, so number 23 we actually just did because we were doing all of this in the previous page. I'm going to let you, as an exercise, sketch the function to confirm that your results are true. Let's go ahead and move on to part B. So as usual with the first derivative test, we're going to start by finding where is the derivative equal to 0 or undefined. So we take the derivative. Okay, and this is a polynomial, so it's never going to be undefined. So we're just looking at where is this equal to 0. So let's see, does this thing factor? Why do I feel like it doesn't factor? All right, give me a second. I'm going to pause the video for a second. Okay, yeah, so this does factor. Sorry, I was having a little, I don't know, my mind's a little fuzzy. Okay, so when we factor, right, the first is 3x squared, last is negative 8, and then our inside terms are a negative 6 and a positive 4, so that works. Okay, so zero product property says that either 3x plus 4 is equal to 0 or x minus 2 is equal to 0. So here we get a negative 4/3, and here we get positive 2. Okay, so we've got two critical values. So we want to think of them sort of in order on our number line. We've got negative 4/3, and we've got 2. And again, I don't really care about the scale here. The point is just to break up our intervals, see our intervals. So we want to pick a point somewhere in the interval between negative infinity and negative 4/3. So let's pick something like x equals negative 2. So I evaluate f prime at that value. And all I care about is the sign of it. So let's see, negative 2 squared would be a positive 4. So I get 3 times a positive 4 minus a 2 times negative 2. That's going to be a positive 4. And then minus 8. So 12 plus 4 minus 8, that's positive. So I've got that the derivative is positive, which tells me that the function is increasing. So I'm increasing from negative infinity to negative 4/3. Now I choose a value between negative 4/3 and 2. If 0 is in there, I like to pick it. So let's choose 0. F prime of 0 is going to be 0 minus 8. That's easy, so that's negative. So since f prime is negative, that's telling me that f is decreasing. So decreasing on the interval from negative 4/3 to 2. And then finally, we pick something bigger than 2, so say 3. So f prime of 3, I've got, let's see, 3 times 9 minus 2 times 3 minus 8. So 27 minus 6 minus 8, that's still positive. So we've got that f prime is positive, and therefore f is increasing. So I'm going to attach it to this one right here. So we're going from 2 to infinity. Okay, so those are my intervals where they're increasing and decreasing, but we're supposed to go one step further and actually classify. So the fact that we're going from increasing to decreasing, so increasing to decreasing means we have a local max at negative 4/3 comma something. I'll go back to that something in a second. And here we're going from decreasing to increasing. So at 2, we have a local minimum, 2 comma something. Now remember that all of these, we're trying to think about sketching the original function f. So we need to figure out what the y-coordinate is on f. So we plug these x values into your function, and it'll tell you the y-coordinate. So let me pause the video again to do that. Okay, so I did a little quick arithmetic over here. I'm not guaranteeing that this is right. I don't have my notes in front of me to double check my answers, and I'm doing it all by hand. I got a local max at -4/3, comma, -112 over 9, and then 2, comma, -12. So my arithmetic is here. If you spot a mistake, sorry about that. Okay, this video is getting long, so I'm going to stop it now.